Hello, class. Hope all is well. Today we are going to look at exponentials and logarithms. We're going to just kind of get an introduction. Try not to take too long. Just want to kind of give you a feel as to what these functions are. Um, they're extremely important, actually, if you go past Algebra 2 or college algebra class and calculus and beyond, because they represent what happens in nature quite often. Exponential growth, logarithmic decay, things of that nature. Um, so what is the exponential function? Well, to define the exponential, we say f of x equals b to the x. And we call that the standard exponential function. We let b here can be any real number. Okay, so this is b for base. This is the base here. B can be any real number, and it actually matters what that real number is in terms of what the function will look like. Now, exponentials are a little different than all the functions we've seen before. For example, if we look at f of x equals x, g of x equals x squared, h of x equals x cubed, and on and on and on. We've seen quite a few of these functions before. We've been able to do something with these in terms of solving equations where they show up. That's going to kind of change here. Okay, this is a little bit weird because notice the x, your variable is up in the exponent, and we really don't have any way of getting at this yet if we're trying to solve for x. And that's what makes exponentials and logarithms a little different than all the stuff we've seen before. This is kind of where functions get a little weird. So first, what I really want to do is kind of look at some of the properties of the exponential. So let's look at an example, and we'll choose a base value. Probably the easiest one to choose first, and there's actually a reason we normally don't choose this. Let's look at some kind of pathological case. Okay, so the reason I call this a pathological case is because something weird is going to happen, right? This is kind of a boring function here because think about it. If we take some x values and we take some f of x values for this function, and we'll just kind of pick a few values. -1, 0, and 1 are always kind of my go-tos. Plug in -1, what do you get? Well, we get 1 to the -1, which is just 1 over 1, which is 1. Okay? Plug in 0, what do we get? Well, anything to the 0 power, as long as the base isn't 0, is 1. 1 to the 0 is 1. And then if you plug in 1, that's pretty clear. 1 to the 1 is 1. And so it kind of seems like, well, whatever value we plug in here, we will get 1, and that's true. So this function is quite boring because its graph just looks like this. Going through 1. It's just a line y equals 1. So a very boring pathological case in terms of what an exponential function can be. We can look at some other kind of boring pathological cases. If we, for example, let g of x be 0 to the x. Okay? Plugging in some values. -1, 0, 1. Again, these aren't all the possible values, but this generally gives you a good idea of what's going on. Plug in -1, well, some really weird stuff happens, right? So we get 0 to the -1, which is 1 over 0, which is undefined. Okay? 0 to the 0, well, that's one of those kind of indeterminate ideas. It can be a lot of things. We could say, well, 0 to anything is 0, but we can also say anything to the 0 is 1. And so in two different ways, we could say this is both 0 and 1, which instead of saying that, we just say this thing is undefined. Then if we plug in 1, we at least get something here. It's 0. But again, it's still kind of a boring function. So for any positive value you plug in here for x, you're going to get 0. And so these are kind of our two pathological cases that we like to stay away from. Another one could be -1. So plugging in -1, you're just going to sit there and bounce around. You plug in a positive value, you're going to get +1. You plug in a negative value, or you plug in a positive, you plug in an even value, you're going to get a +1. You plug in an odd value, you're going to get -1, and it's just going to kind of sit there and bounce around, and then weird stuff's going to happen in the middle of those. So we kind of have these pathological cases we like to ignore. And so for the most part, we'll just say, like, we want the base to be something nice. Pretty much any whole number, a fraction. And there are also some other numbers called transcendental numbers, whether we'll let them be actually very important transcendental numbers. But for the most part, we want those to be nice numbers. Okay, and so let's kind of think about, let's look at some examples of nice ones, non-pathological cases. Let's see here. Okay, so we want B to be, what did we decide? We want B to be greater than 0 because weird stuff happens at 0. So let's restrict our domain for a second. Well, not our domain, but what this B value can be here. Let's restrict what it can be. Let B be greater than 0, but less than 1, because again, weird stuff happened at 1. And weird stuff happens in the negatives also, so we're going to ignore that. And then also, we're okay with B. So let's kind of restrict B. Let B can be greater than 1 also. Okay, and these are actually two special cases here for what B can be and what the function will look like. Notice if B is in here, it's going to be a fraction of some sort. And if B is greater than 1, we're going to have some kind of growth happening. We'll see that in a second. So let's look at some examples of this happening, non-pathological cases that we're okay with. Okay, and this is kind of how, this is actually how the exponential is defined. And there's a reason for that. We saw that in the pathological cases. So let's look at some nice examples. If we let f of x equal 2 to the x. Okay, so now we actually have something that can happen here, and something that can give us something that's worthwhile. Take some x and some f of x values. Okay. Again, let's plug in some numbers. These are just kind of the standard ones I go with. You probably want to plug in more to get a better idea of what's going on, but for me, these are usually good enough. Plug in -1. We get 2 to the -1, which is just 1/2. If you remember your exponent rules, any negative exponent it'll reciprocate the number. Plug in 0, we get 2 to the 0, which is 1, because anything at the 0th power is 1. And then plug in 1 and we'll get 2. Okay, and so if we try to graph this thing, -1 maps to 1/2. So -1, so we'll say -1's here, and then here's 1/2. 0 maps to 1, so 0 here will map to 1. and 1 maps to 2. So 1 maps to 2. It kind of makes sense here. As we plug in larger positive values here, this thing's going to grow very quickly. And so we kind of expect something like this to happen. Okay, and we can see here as we head in the negative direction, what this is going to do is it's going to reciprocate this. Okay, and it'll take this value, reciprocate it, and multiply by some value. And so the denominator, as x gets small in the negative direction, this value is going to get, the denominator of this value is going to grow. And when the denominator grows in a fraction, the number gets smaller. And so actually it's going to kind of decay just like this. And so graphically, we're looking at something kind of like that, more or less. And this is one of the standard cases of the exponential. And it turns out that if you let this number here, as long as it's greater than 1, it'll look like this pretty much every time. Okay. As this grows, this will grow faster and this will decay faster. But for the most part, in terms of just graphically, just kind of being like, okay, I have an idea what this thing looks like. It doesn't matter. As long as it's greater than 1, it'll look like this. Okay, so let's look at another pathological case. So we'll just write to the side here. For b greater than 1, graphically, this thing's going to look like this. Okay. Now, the second pathological case, or non-pathological case that we're going to look at, is something like this. I keep calling everything f of x, but it doesn't matter. Let's pick 1/2 to the x. Okay, and if we simplify this, this is just 1 over 2 to the x, just to give us an idea of what's going on. Again, let's do our little chart. Probably shouldn't have called it f of x, but it's okay. Plug in a value. Well, what's going to happen, if you kind of see the symmetry here, see the symmetry that's going on here. This will map to what mapped to 1 here. So -1 here will map what 1 mapped to over here. So we're just going to get 2 here. And that's because that's 1 over 2 to the -1, which is just 2. Plug in 0, we're going to get something similar. It's just going to be 1 over 2 to the 0, which is just 1. Okay. Plug in 1, we're going to get 1 over 2 to the 1, which is just 1/2. Okay, so we're going to get something that looks really similar here. I'll graph it up here. Run out of space. X. Let's get our x values on here. -1, 0, and 1. Just a real quick sketch. -1 maps to 2. So 1, 2. 0 maps to 1. And 1 maps to 1/2. And we can kind of see what's happening here also. As we grow in the positive direction, this is just going to become a smaller and smaller fraction. And so this is going to decay this way. And as we head in the negative direction, it's going to reciprocate it, making it a whole number. And it's going to go to infinity here as we let x get really small in the negative direction. Okay, and this is actually an important case. This gives us an idea of what's going to happen for all values that are in between 0 and 1. So we actually know what this thing looks like now. It's going to always look something like this. And yes, it is just a reflection of this. And that's always true. Okay. Now, let's look at an equation involving an exponential. I want to kind of give you an idea of the problem. The problem with exponentials and why we kind of wait towards the end of college algebra or algebra 2 to talk about these things because they're kind of weird. So first let's look at something that we're used to. So for example, 3x plus 2 equals 4. Okay, and we want to solve this thing. Well, it's fairly straightforward, right? We know how to do this. Subtract 2 from both sides. You're going to get 3x equals 2. Divide both sides by 3. We're going to get x is just 2/3. Okay, and we have this very easy, nice way, at least algebraically, to solve for these for x here. But now let's look at an example with an exponential function included. So let's do like 2 to the x plus 4 equals 8. Okay, seems fairly harmless, but really think about it a second. How would you try to solve this? Well, subtract 4 from both sides. We know that, right? Like that's not going to change. We're trying to isolate the x value. But then what do? Right? So some of you, if you're rather clever, can maybe just think about it for a second. Instead of trying to stick to an algebraic principle, just think of it intuitively, right? So what is this asking? This is saying 2 to what equals 4? Well, hopefully we have that in our head already, but maybe it wasn't that clear to think of it that way. But for now, it's good enough just to think of it that way. 2 to what power equals 4? Well, if we just kind of over here and do a little scratch work, hopefully it's not a ton of scratch work, 2 to the second power is 4. Okay? So we can just say that this kind of tells us that x must be 2. Okay? So hopefully that isn't too bad. That's the end of this lesson. Really, we just kind of got an intro to exponentials. But really, the question remains, what if it's not this nice, right? What if there's fractions involved? And what if there's ugly stuff going on? What do we do? Well, that's what logs are for, okay? And so just for this video, we'll end it here. We need to know what to do with exponential functions, or when exponential functions show up in equations. We need to know what to do and how to solve for x when it's in the exponent, and maybe our intuition just isn't there. Maybe there is no intuition to be had. Maybe it's just too difficult. How do we solve for that value?